recently I've been wondering and kind of thinking about much of the work that I've been doing for the last 25 years. And I realized that it has to do with the limits of science and engineering. Also, I didn't realize until recently. So, of course, I guess everybody would agree that, let's say, we need to be aware of our limitations, because on the one hand, this will prevent us from bumping into them, from crashing into our boundaries, but also gives us better tools to try to go beyond them and try to develop new methods for this. And all of this is part of the scientific process. So, I mean, of course, this is not something new. So, of course, the limits I will mention is the ones that we can identify now. And of course, we would like to develop new knowledge to go beyond some of them, but probably some of these limits we just have to accept. So I will mention some of these because, of course, this is not an exhaustive list. So first limit would be non-stationarity, that it's simply a consequence of change. So, of course, we have so many mathematical tools to understand and describe dynamics, but then the way in which systems change can also change, and then the way in which systems change can also change. So we can have different scales of dynamics, and at the end, if we want to have a full description of the world, we'll find that we're always encountering never before seen situations, and also these situations will never be repeated. So this limits predictability in a particular way. And one way to deal with this is with adaptation. That, I mean, cybernetics was developing already for 75 years, different techniques and methods to try to build adaptive systems. And this was also the goal of artificial life since the 1980s, and also in cognitive science, trying to understand how we adapt to different unforeseen circumstances. And of course, then we can build adaptive systems. A more important limitation of science that has to do with complexity, we can call non-reductionism, in the sense that we cannot have shortcuts to the future, because interactions in a complex systems generate information that it's necessary to reach the future. So technical term is computational irreducibility. And this again limits our prediction, but in an inherent way, because there's no shortcut to the future, but to go through all the intermediate states. And if these states have never been visited, then it's like, okay, how do we reach the future if it's not a posteriori? And one way in which we can deal with this is with self-organization, that many of the people here have worked with this. So this is an example that we developed a few years ago with a PhD student and a colleague back in Mexico, while comparing self-organizing traffic lights and autonomous vehicles. And the key of self-organization is that instead of solving a fixed problem, we can design interactions of the components of a system so that when the problem changes, the system can adapt by itself. So this is a way in which we don't need to predict, but we can still, in a limited way, build adaptive systems that we can see that in practice, their performance is much better, in some cases even better than the theoretical optimum. So there's some work we have about superoptimality in public transportation systems that illustrate this nicely. And this non-reducibility, it's related to limits that complexity exhibits, or let's say by studying complexity thanks to computers, we have been encountering these limits, although some people prefer to ignore them, assuming that they are not really problems and we just need more computing power, faster computers, of course, more funding. That we all agree on that. In order to be able to predict the future. But there's the property of strong emergence, which is characterized by downward causation. Even if, let's say, we don't believe in strong emergence, but of course it depends on who you speak of. One example of strong emergence or downward causation in a social system, you have individuals and then they develop social norms, and these social norms define or have causality on the behavior of individuals. And of course, this is not a material level, it's at an informational level, but there is a causal chain from the higher scale to the lower scale. And we could enter a philosophical discussion on whether downward causation is real or not, but then that's more appropriate for a talk on the limits of philosophy. So I will just say that in practice, so this is for science, but also for engineering, we cannot, in practice, we cannot define or predict what will occur at the higher scale if we don't consider the lower scale, but also we cannot even predict the lower scale if we don't have information at the higher scale. So this is downward causation. Another limitation would be deterministic chaos, which is characterized by sensitivity to initial conditions. And this, again, limits predictability, but in a different way. And it's interesting that we can have chaos and complexity, or just one of them, or neither. It seems that in practice, it's easier to deal with the limits of predictability imposed by chaos, but it's useful to be aware of this limitation as well. But I won't go deep into it. I think that a more important limitation is that of non-computability, which has to do with combinatorics. And of course, we have to distinguish computability in theory and computability in practice. So Alan Turing defined computability 1936, trying to prove, well, not trying, by proving that formal systems are not decidable. So it's a mathematical problem posed by David Hilbert, and he defined what's a computable function. But this assumes infinite memory and infinite time. So we have computable functions in theory that in practice are not computable because we don't have enough time in the universe. And on the other hand, we have non-computable functions in theory that in practice they're computable because a posteriori we have enough information to be able to calculate, let's say, the halting function of some Turing machines. So many of you might be familiar with this allegory of monkeys randomly typing on a typewriter and eventually producing complete works of Shakespeare. And this sounds feasible because, okay, we assume infinite time. But then I was speaking with my eldest daughter, and let's just, for sake of the argument, let's do the numbers and see not complete works of Shakespeare, just first page of Hamlet, 500 characters. If we had the most powerful supercomputer producing combinations of letters, let's say, so really fast monkeys, from the Big Bang until our present day, how many characters of the first page of Hamlet would we have so far? And the answer is 17. So, I mean, the combinatorics is such that by random processes, you will never get the complexity that we observe. And of course, this tells us that our world is not random, which we know. But let's say, if computation is limited in practice, there are many things that in theory make sense, but in practice are unfeasible. So, for example, most of all possible chemical reactions in the universe will never occur. There are just too many. Still, evolution has managed to produce life, just exploring a tiny fraction of all that possible space. In a similar way, all the possible states of our genome, having a Boolean simplification that genes are on or off, would be 2 to the 16,000. And of course, that has not been explored minimally, not even for humans, not for any species. So in spite of that, evolution doesn't need to explore exhaustively search spaces, but just with a minimal amount of search, evolution is possible. So even when the current configuration of atoms will never be repeated, regularities are such that we can have some limited prediction, but this doesn't mean that we will be able to predict everything. So how much can we predict is something that, let's say, we should consider in order to be able to measure how much can we say, how much can we predict, how much can we know. And of course, this resonates with Wigner's paper on the unreasonable effectiveness of mathematics, because when we start calculating these numbers, it's actually surprising that we can do so much. And of course, by doing so much, sometimes we assume that we are able to do everything in theory, but again, in practice, we know that there are many limits. And a few years ago, in the last wave of AI, I was starting to think about its limitations. And I mean, these images are classic examples of, let's say, computers confusing different images. And working with a PhD student about data of students in Mexico City, tens of thousands of students, and trying to predict the probability of finishing on time their bachelor's. I mean, by just analyzing the data sets, we realized that there were some students that had exactly the same variables after 1 year of studies. And some of them would finish on time in one category, and some wouldn't finish on time. So I realized that this is a problem not of the algorithms, but of the data sets. If you have overlapping data sets, like in this case, then it doesn't matter how good your algorithms are, how much data points you have, your classificability will be limited. So this is something that we're finishing a draft. And if you are limited with that, then what do you do? And of course, AI will be limited, and we can actually calculate the theoretical limit. I mean, I don't know what alternatives we have if we have this inherent data limitation. And in some cases, having more data can even give worse results than having less data. And I mean, of course, there are other problems in statistics, like spurious correlations and so on, that also can show up in artificial intelligence. I will mention briefly other limits. So in social sciences, like psychology and sociology, there have been recent crises of non-replicability of classic experiments. In operations research, there are problems that we cannot optimize, on the one hand because they're changing, on the other hand simply because their search space is too huge. So again, we cannot explore it fully, and all the search methods we have not necessarily will give us the optimal solution. There are problems that we cannot really define, and then there are the things that we don't even know that we don't know, and the things that we can't imagine. I mean, I don't know whether these are already scientific problems, but we can see that there are many limitations to our to what we can know. And again, touching a bit on the limits of philosophy, where there's this distinction between epistemology and ontology. Epistemology studies how we know, and ontology how things are independent of an observer. Traditionally in science, we try to be objective, which makes sense because different perspectives can give you different answers. But at the end, we know that we cannot describe anything if it's not from an observer's perspective. And I mean, this was already noticed in cybernetics. And of course, we cannot have an epistemology without an ontology. And I mean, not to go deep into this, I'll just quote Schrödinger. The world is given to me only once, not one existing and one perceived. Subject and object are only one. The barrier between them cannot be said to have broken down as a result of recent experience in the physical sciences, for this barrier does not exist. So all I want to say is that we need to accept that purely objective science especially that which involves observers like psychology, even more science of consciousness, is not possible. But then what do we do if we want objectivity in science and we cannot get objectivity? What should we do? And also, because of time, I won't go into the limits of formal systems, but let's say much of science is based on mathematics, and mathematics has its limitations. So, for example, it's shown that you cannot have in a formal system at the same time completeness, consistency, and universal computation. You can have 2 out of those 3. And then in some cases, we stick with consistency and universal computation, but then that gives you incompleteness, and then that gives you some problems. But then if you, I mean, that's worse than not having consistency. But then just to quote Alan Turing, he wrote in his 1950 paper about whether machines can think. He noted that if we expect machines not to make mistakes, then they cannot be intelligent, because in order to be intelligent, they need to make mistakes and then to learn from those mistakes. So in a way, Hilbert's program trying to prove that mathematics was complete and consistent and decidable seems to be like a failure, but it seems that maybe we should be happy that our world does not fit with those presuppositions, because in such a world, there wouldn't be possible for novelty, for creativity, for evolution. So I just list here some of the limits that I mentioned. There are more and potential solutions. So for non-stationarity, we have adaptation. For non-reductionism, we can use self-organization. For non-compatibility, people use evolution. For let's say genetic algorithms as different search. For non-classificability, I have still no idea, because it's some inherent limits in the data. And I mean, this classification of problem solvings, I mean, if a problem doesn't change and it's easy, then we don't even call it a problem. We just solve it and that's it. If it's difficult, then as long as the problem doesn't change, if we are perseverant enough, we'll eventually find a solution. And then if the problem is easy and there is change, we just build adaptive systems that will adapt to that change. But then if the problem is difficult and it's changing faster than we can even understand it, then we should just accept that we won't be able to solve it. And in many cases, it's better to have some humility on the problems we cannot solve, rather than assuming that we will be able to solve and then not doing it. And I mean, many of these limits will not be overcome, especially those of formal systems. It's proven that there are limits. I don't know whether we can come up with novel formal systems that can go beyond these limits without losing the aspects of formal systems that we want. And perhaps some of these limits we should just embrace, because they have this richness. As I mentioned, if we had full predictability, then we wouldn't have creativity, and maybe we don't want that. I mean, of course, we would like to predict everything, but it would be worse not to have creativity. So just to conclude, better to accept than ignore limits in science. This has implications for engineering, and there's so many things to explore. So thank you.
Very well synchronized.